perhaps the most important part of a space voyage is coming home safely. The spacecraft must survive the extreme heat and friction of re-entry into the Earth's atmosphere. Scientists and engineers create heat shields to protect the spacecraft. But how do they know it will really work? The answer is the ArcJet facility. For decades, this laboratory recreated the heat, gases, and chemistry experienced during re-entry, giving us the confidence to fly, explore, and return home from space. The ArcJet combines heat, the proper mix of gases, and the chemistry that occurs at extreme temperatures to simulate the flow experienced by spacecraft during their fiery re-entry through Earth's atmosphere.
So when you're coming back from low Earth orbit or even the moon, you're coming back at very high velocities. And so from coming back from low Earth orbit, you're on the order of 7 kilometers a second. From the moon, you're coming back about 11 kilometers per second. That's really fast. And so when those vehicles actually encounter the atmosphere, then they're just essentially slamming right into that air. And so that creates a shock wave around the vehicle. And right behind that shock, that kinetic energy associated with the reentry is converted to chemical energy. So you take the basic air, it's mostly nitrogen, about 77% nitrogen, about 23% oxygen. And so what happens is when you go through that conversion process, going to kinetic to chemical energy, what you're doing is you're breaking apart the molecules. And so at first is going to go as the oxygen, then it's going to go the nitrogen. So as opposed to an oxygen molecule or a nitrogen molecule, now you'll have atomic oxygen or atomic nitrogen. And atomic oxygen can be very, I'll call it corrosive, because it really just eats up material. So all that gas on the other side of the shock, on the vehicle side, then encounters the thermal protection system. And so that's how you have to know, well, how does that gas affect that thermal protection system? Is it going to protect the vehicle? And of course, the only way we know how to simulate that on the ground is through these ArcJet facilities.
Because we do not know how a material will behave until it gets in these facilities. There's no analytical equivalent to an ArcJet. We have math models and we have tools, but they require ArcJet testing to benchmark them and to provide the core properties for those tools. So there's a lot of materials that might perform well in a strictly thermal environment, such as blowtorch, but will not perform the same in an ArcJet or in flight because of this chemistry of the flow field.
So the basic operation of the ArcJet is to simulate the reentry environment. The nuts and bolts of it is you want to take gas and just take it to a very high energy level. And the heater is the workhorse of the ArcJet facility. So all the components come together to make the test work, with high pressure water cooling for the cooling of the segments, to the test gas, the nitrogen and oxygen, to the electrical power, and then into the vacuum system for testing the material. Okay, so when we receive a model, typically the models come with thermocouples already attached. And then in the test chamber, we have 2 hydraulically actuated sting arms. So we would establish our flow field, and then the model is on a sting arm would be rotate into the flow. We would test it. And then we would rotate it out of the flow field. So on that sting arm is where all the data hookups are. So we would run that to our data system. During the test, we get all kinds of additional data. We would test these types of ablators, typically up to 3,000, 4,000 degrees Fahrenheit, even higher. We would test them at very high temperatures for different types of trajectories. Primarily for the lunar is what gave the highest types of heating rates and correspondingly the highest temperatures of the surface of the model. For a ISS type of reentry, the heating rates are a lot lower, so we're talking about 2,000, 3,000 degrees. But for a lunar type, very ballistic type of reentry, you're about 4,000 degrees, even higher than that.
The use of the ArcJet began in the 1960s for the Apollo program. scientists and engineers needed to test the heat shield material for the Apollo spacecraft, which would be returning to Earth at unprecedented speeds.
As you know, we had to develop an Apollo heat shield material. And to do that, we actually tested several different ablator materials from different companies. Well, we did learn several things, that there are certain ingredients that you can put in the material that do not enhance its performance. In fact, one of the materials that we actually tested, the big claim by the company was the ingredient that they put in it was what really made it great. We tested that material with their so-called magic ingredient, and we didn't get very good results. However, we took the ingredient out of the material, retested it, and it was much better. So the facility allows you to test those things and make judgments on the material itself. Absolutely. The Apollo material, because of the ArcJet testing, went from a high density material of around 60 pounds per cubic foot all the way down to around 32 pounds per cubic foot by the addition of some fillers, we call them, within the material. And we still got really good performance. We got good temperature performance, we got good installation performance, and we got the good surface performance that we wanted from the ablator itself. So absolutely, you can test a material with various compositions and make good judgments on how that composition changes that material under these conditions of pressure and temperature.
As the Apollo program ended, the ArcJet was called into service once again to test the thermal protection system for the space shuttle. Unlike the Apollo spacecraft, which was a one-use vehicle, the shuttle spacecraft would be used again and again for multiple flights. Its thermal protection consisted of new lightweight tiles and reinforced carbon-carbon shielding for the nose and wing leading edges.
I was the manager on the carbon system, which was the high temperature portion of the orbiter thermal protection system. And because we needed to go to high temperatures, which was the hottest spot on the vehicle, we could test temperatures in excess of 3,000 degrees Fahrenheit on the surface of the material, which allowed us to develop performance curves, performance analysis, limits of the material's performance, just about anything you wanted to know. Early on in the carbon program, we uncovered, along with some testing done at Ames Research Center, a phenomenon that we called oxidation between the coating of the carbon, which was silicon carbide coating, and the carbon substrate, which is basically carbon. We had what we call pinhole formations between the interface, which was not satisfactory because we could lose the carbon coating system due to lack of strength between the coating and the carbon silicon carbide coating. That was a very important finding between Ames and Johnson Space Center in ArcJet testing. As a result of that, we developed a system called the TEOS system, tetraethyl orthosilicate, which we could infiltrate into the porosity of the carbon system, which then protected this formation of these so-called pinholes.
For decades, work continued with the ArcJet in service of the space shuttle, both testing for improvements of the thermal protection system as well as for unexpected events.
Yeah, very memorable tests for me was after the Columbia accident. Obviously, it all hit us very hard, and we immediately came into this facility to help understand what happened during that accident. At that point in time, we knew that we actually had a hole in the leading edge of the orbiter. And so what we did is we put a hole in some aluminum plates, and we put some big, thick cables behind that. And what we were trying to do is trying to understand how the flow could be ingested through a hole and then destroy some of the cabling that controls the vehicle itself. And so we actually set up that process and actually did those ArcJet tests here. And it helped us get data to correlate to our models so we could better describe what happened during the accident itself. So those are some very important tests that we did, and very quickly, and were very important to understanding. And all of that is documented in the CAVE report. STS-117, where we had a blanket that was detached partially from from the OMS pod, which is back on the back towards the tail of the orbiter, and we could see it. We were concerned about how to repair it, and so some innovative folks said, hey, we got these medical staples on board. We can send an astronaut out there and use this staple gun to stitch this thing back together. But what we didn't know is, well, what happened with the staples during re-entry? Would they just disintegrate and then the repair would be worthless?
Did that test, and that repair worked beautifully. We had camera on it. Steve did a good job setting up a camera, and we can see the staples glowing. We can see the pins glowing, and they decide, yes, do the EVA, and it worked great.
Another mission was STS-118. We saw some ice damage to a tile, and so we said, hey, we're really concerned about this. Is this going to cause a problem during re-entry? So we actually machined a damage into a tile. We did several tests. So we did those tests, convinced ourselves that we'd be okay during re-entry, and lo and behold, the vehicle did come back and without any problems whatsoever.
The ArcJet proved time and again the importance of testing materials to see how they would behave during re-entry. The data gathered and the lessons learned from the ArcJet live on every time a spacecraft returns its crew safely home to Earth.